And we're back. Welcome back from the weekend and happy Tuesday. Today we're going to switch gears and look at properties of variance and covariance. But before we begin, let's focus on some administrative bits. Project number 2 has been posted to the course Blackboard. It is due Tuesday, the 6th of October at the usual 11:59 and 59 seconds, 1 second before midnight. The reading has changed. The reading, sections 3.3 to 3.4 in the Barron text by the 13th of October, pages 47 through 67. As usual, please make sure you are keeping up with the reading. Do something every day for this class, at least 1 hour per day. So, when we last left off, we talked about expectation and we talked about variance. We explained that variance was a measure of the magnitude weighted by probability. So it's a probabilistic average of the magnitude, but not the direction of the difference between each measurement and the center, the mean. The variance had an issue, and the units are squared because of the square term. And the standard deviation fixed that up, putting it in the same units as typical measurements or the mean. So we also talked about the coupling between variables, random variables that could be in a vector. We gave an example from the economic growth curve and the world oil production. And this is our covariance. It's a weighted by the joint probability of the difference between each measurement with respect to x, with respect to random variable y. We multiply them together. Covariance had this weird issue of its value and its units. So we normalize this in a sense, the same way you place something on a percentage scale to give us correlation, which takes this covariance and puts it between a +1 to -1 scale. And now this correlation allows us to make comparisons between two systems, even though the random variables might have units that are different. So let's look at properties. Now, before we do this, let's have a little bit of a refresher, and this is the only time I'll spend time doing this. We have a bunch of rules as it pertains to algebraic operations. We have the so-called associative rule. What the associative rule says, it says if I have two numbers, A, and I add it to B and add to C, I can choose to group together these operations and it's the same result. So I can take A and B and add them first, get that result, and then take that result, add it to C. Likewise, I can take B plus C, add them together first, as is noted by the parentheses, and then take that result and add A to that result. So this associative rule we can make use of as it pertains to summation. So when we have our summation, let's suppose we have, or I goes from 0 to big N, and we're summing together what we're going to call these measurements xi. Well, that's just the same as x1 plus x2 plus x3 and so forth up to and including plus xn. Now, when we do this associative rule, we can associate maybe this part with that part with that part, two at a time, and then sum those sums. Let's take a look at another type of summation. Let's say we said I goes from 0 to n, and we said xi plus yi. And so in that particular case, we have the following expression: x1 plus y1 plus x2 plus y2 plus ... all the way up to and including xn plus yn. Now, here, we're associating the sum of the x and y first, and then we're taking that result and summing them together. So here's the x and y, here's the x2 and y2, xn, yn, take those sums, and then take that sum, add it to that sum, to that sum. Now, the associative rule allows us to group these differently. Instead, we can say x1 plus x2 plus xn, and then take that and add that to y1 plus y2 ... plus yn. When we do that in summation notation, we'd write I goes from 0 to n, that should be 0, 0, and there should be a y0 here. I goes from 0 to n of xi. We do that sum first, and then we say change the variable j goes from 0 to n of yi. And so the associative rule allows us to regroup things in a sum. Let's take a look at the distributive rule. The distributive rule says if I have A and I multiply that by some sum B plus C, well, I can distribute this multiply by operation. So I take this A, multiply it by the first term, multiply it by the second term. So that first term is A times B. The second term is B times C. So I take those products and I add them together. So this distributive rule allows me to distribute this multiplication over this summation. Now, the converse of that, it also allows me, if I have such, that should be A, if I have such an expression, I can factor out this A and write A times quantity B plus C. And so I'm making use of the distributive rule in order to do this factoring. Okay, so that's my distributive rule. Okay, so what does this mean? Suppose if I have a summation, I goes from 0 to n, and let's say I write A times xi plus yi. Well, what can I do with that? I can distribute this multiplication by A to each term inside the summation. So that gives me sum I goes from 0 to n of axi plus a yi. Now, of course, I can take this and I use it in the opposite direction. I can factor out an a. I can say a times, using that distributive rule, times that sum of xi plus yi. Now let's take a look at this expression in the middle. Well, we just said that we can use the associative rule. So I can literally break this apart to say this result is just a times summation I goes from 0 to n of xi plus summation j goes from 0 to n of yi. All right, so this is the distributive rule with summation. Let's turn our attention lastly to multiplying factors, the so-called FOIL rule. Suppose if I had x plus 2y times x plus 2y. Well, the FOIL rule you learned a long time ago: first, inside, outside, and last. And it gave you a prescription for how to multiply two factors. Okay, so you said the first, x times x squared, inside, or it should be outside, first, outside, inside, last. So the outside, that's first is x squared, plus the outside, that's x, 2y, 2xy, inside, 2xy, last, 2y times 2y, that's 4y squared. And so I add this up, I get x squared plus 4xy plus 4y squared. Now, in other texts, you'll talk about squaring and cross terms. Now, the inside and outside, those are the so-called cross terms. And so what we'd say, you take the first item, you square it, x squared. You take the second item, 2y, square that, 4y squared, and then you multiply the cross terms. You say 2 times the cross term, so that's x times 2y, that's 2 times 2xy, 2 times 2xy is equal to 4xy. That's 4xy. And so this idea of the FOIL rule is how you multiply factors. And these factors, it could be something simple like x plus 2y, or it could be something like x plus 1 plus y plus 2. And we say quantity squared. In that case, this takes the place of my first term, this takes the place of my second term. So I could say x plus 1 quantity squared plus y plus 2 quantity squared. That's first thing squared, second thing squared, plus 2 times the cross terms, first times second, plus 2 times x plus 1 times y plus 2. So again, I'm applying the FOIL rule, or the first squared, last squared times 2 times the cross terms, in order to multiply these factors. So we're going to use all of this, and we're going to use all of this to help us with some expressions to give us identities, properties, as it relates to the variance and the expectation for different transformations, operations we can perform on random variables. So here's our expectation, and we said the expectation mu is just the weighted sum of the outcome of the variable, values it can take on, times its probability over all possible observations. And so this idea of linear expectation talks about multiplication by a scalar. It changes. How does it change? So if you have some measurement x and you multiply x by a value like 5, how does the expectation of that value change? Well, here's our first property. It's called linearity of expectation. If you have random variables x and y, and you multiply x by scalar a, y by scalar b, and you add a scalar we're calling c, well, the expectation of this transformed version of the variables is equal to a times the expectation of x plus b times the expectation of y plus c. Now, sometimes notationally, when we write expectation is mu, but we give a little subscript like x, meaning it's the expectation of random variable x, or mu sub y, to mean that it's the expectation of random variable y. So we use this notation just to make it easier to understand expectation of what, or with respect to what, probability of x or probability of y. So let's take a look at this expression. So we substitute what expectation means, and in this particular example, we have two random variables x and y, and we're transforming them with a function that multiplies x random variables value by a, b's by y, and it's taking that sum and adding c to it. So let's look at this expectation. So we have a double summation then, because we have a joint probability. We're involving two random variables. So one of these summations is indexes all the values that x can take on. The other indexes all the values that y can take on. So what does expectation mean? You have the outcome times the probability of the variables. So here we have the outcome, which is this function, whatever value it is. So we have ax plus by plus c, and the probability we're weighting it by as we sum is the probability of the random vector xy, those instantiations that x can take on, and at the same time y takes on. So now, okay, we take a look at this, and now we're going to take advantage of the distributive law. Here, we're multiplying by probability of xy, right? So we can distribute this multiply by probability of xy to that third term, to that second term, and to that first term. So we can now take p of xy times the first term, p of xy times the second term, plus p of xy times the third term. And the distributive rule, distributing multiplication over addition, allows us to do that. So we write the first term, ax times p of xy plus by times p of xy plus c times p of xy. Okay, so now what we're going to notice is that we have a summation. We have a sum of a first term with a second term and with a third term. And then each of these is summed for each instantiation for x and y. But we're going to group these together. We're going to group them first using the summation and not the individual terms. And that's very similar to what we said when we had that summation on the previous slide, where we talked about this particular transformation, this one, right? So we're going to take advantage of the associative rule, and we're going to take all of the values of x and y for the first term, and we're going to add them together, and then we're going to take all the values of x and y for the second term, add them together, and do the same for the third term. So if we do that, now we have the summation over all values of x and y for ax times probability of xy, plus the sum all the instantiations for x and y for by times probability of xy, plus the sum for all instantiations of x and y of c times probability of x and y. So now the observation we make is, oh, wait a minute, I have a scalar here multiplying each one of these terms. And remember, it's summed. So I can take advantage of that distributive rule and factor out this a from all of the terms summed together for x times probability of xy. I can do the same for by times probability of xy and c times probability of xy. So I do that, and I can pull out effectively this a. And I'm just going to pull it out of that first summation with respect to y, because I can do that. I'm going to do the same thing for b, and I'm going to do the same thing for c. And now here, in this last example for c, it doesn't matter what I pull it out. I'm going to pull it out of the entire summation. I'm summing over two different types of values. But for the a and the b, I'm only going to bring them out from underneath the y summation. I could have equally well have brought them out from under the x summation. So now I'm going to take advantage of something that we talked about before. Now, we talked about this idea of marginalization. And when we marginalize, we said we were going to sum out all the values that one of the variables can take on. So here in this first term, you notice I'm summing out with respect to y. Now I'm going to take advantage of that. But before I do that, I'm going to bring out this a because it is a constant underneath that summation with respect to y. But I also notice this x here. This x is a random variable, but this random variable, when I look at this summation index, it does not vary the values of x. So for all intents and purposes, x looks like a constant underneath this summation. So it looks like a constant, and I can take advantage of the distributive rule, and I can factor that out under all those terms that vary in y. Because this summation index only varies our y. So I can bring out the x also, in addition to factor out that a. Likewise, for the second term, I can bring out the b, but I can also bring out the y term, rather the y term, out from underneath the summation with respect to x. And it doesn't matter if I sum the x's first or I sum the y's first. I can reverse these summations to be summation of y and a summation of x. So if I do that, I can bring out this b and y from out of this summation indexing over all the values of x. So I get the summation with respect to y, I have by, and I have that summation with respect to x. Likewise, c, it's a constant. And as a constant, it does not vary, and I can factor that out because of the distributive law of multiplication over addition. Okay, so now I get this expression, and now I'm going to make use of marginalization. So here I'm going to marginalize, because here I have the sum over all instantiations of y, probability of xy. So that's going to give me probability of x. I'm marginalizing, getting rid of all the values of y. Here, I have a summation with respect to x. So I'm going to look at all the instantiations of x, add them together. I'm marginalizing with respect to x, and that's going to give me probability of y. And then lastly, if I look here, I'm summing for all the values of y, all the values of x, all the probabilities associated with my joint probability of xy, p of xy. Now, of course, law of total probability tells me that this is 1, because every probability sums to 1 if you add up the probabilities of all the possibilities. So that's just c times 1. So what that leaves me with, I have my summation x, I have my ax, and this now becomes the marginal probability p of x. I have my sum with respect to y, I have my by, that comes down, and this becomes the marginalization. I marginalize out x, so that's times p of y, and then I have c times 1, which is just c. So if I look at this expression, I take advantage of the distributive law of distributing of multiplication over addition, because here's my summation, and then here's my multiplication by a. I can bring this a out, so I have a times the sum of xp of x, plus b, I bring that out as well, for the same reason, b times the summation yp of y, plus c. So I look at this, and I say, oh, wait a minute, Well, x times p of x summed over all values. That's just the expectation of random variable x. Likewise, the sum for all values of y times p of y, that's just the expectation e of y. So I make that replacement. I have a e of x plus b e of y plus c. And there's my statement that I set out to prove. And so here we're literally applying basic rules of algebra, the associative rule, the distributive rule, with our summation notation, as well as some of the rules of probability about total probability when this term went to 1, as well as marginalization when we converted this expression to p of y, and we converted that expression to p of x. So we're just using definitions here. So another property, the multiplication of the expectations. The expectation of the multiplication of random variables is the product of the expectations. It says if I take random variables x, y, and I multiply them, the expectation of this product of random variables is the same as the product of the individual expectations. So let's look at this. Expectation of x, y, again, we apply the definition of expectation. We have this part, which is a product, that's our value. So we say xy times the probability associated with those random variables x and y at the same time, times p of xy. Okay, so that's another property, and we could actually do this property out, but let's take a look at it. So let's assume that x and y are independent. So e of xy is xy times p of xy. And p of xy, if x and y are independent, that's just property of independent variables. That's just p of x times p of y. So now we have this expression. And if we look at this summation, that inner summation, it involves an index x. So everything here involving x, that's our value x and our p of x, we can bring out because they look like constants underneath that summation. We're taking advantage of the distributive rule for multiplication over addition. So if we bring it out of that inner summation, that becomes x times p of x, and that's going to be multiplied by our sum y p of y. Now, if we take a look at this, well, this term, that's nothing more than e of y. So that's going to give us this expression. That's going to give us the summation of x times p of x times the expectation e of y. Now, if we look at this term here, that's just nothing more than e of x. Our result is then e of x times e of y. And that's exactly what we set out to prove at the outset. So that means that if you have two random variables and you compute their product as an operation, and you want to know the expectation of that result of multiplying two random variables, that result is going to be the same as the expectation of the individual variables, but you multiply the expectations. So let's take a look at the variance. Now, the variance, we said, of x is the expectation of x minus its center, e of x quantity squared. And we said this was x minus mu quantity squared times p of x. So if we have two random variables, x and y, and we're going to transform them by multiplying x by a scalar a, multiplying y by a scalar b, and then adding c, we're going to prove that that's equal to a squared times the variance of x plus b squared times the variance of y plus 2ab times the covariance between x and y. So let's take a look at this. Let's set up the variance. So the variance says we take the quantity, subtract the mean, we square it, multiply that by p of x. So the variance of this expression, we take that expression, ax plus by plus c, we subtract the mean of this expression minus the expectation of ax plus by plus c, and we square that. So here's our quantity squared, multiplied by the probability, the joint probability p of xy. Okay, so now let's take a look at the expectation. We just got done talking about linearity of expectation. So here we have e of ax plus by plus c. We negate it. That's nothing more than e of ax plus e of by plus e of c. We negate them, so we say minus a e of x minus b e of y minus c. So this is an exact application of linearity of expectation that we had from the previous slide. But we have a leading negative, so everything has a minus sign instead of a plus sign. So now we have this expression. We still maintain that quantity squared multiplied by probability of x, and we have our leading summation. So the next thing we do then is we apply our expectation. We're just evaluating. So E of x is going to be mu, and we're going to write mu sub x. So we'll remember that's the expectation of x. And E of y, we're going to write mu sub y. So we'll remember that's the expectation with respect to y. So if we take this, we're going to group together terms by associating these subtractions. So we have ax and we have a times mu x. So we're going to group them together. So we write ax minus a mu x. Do the same thing for the y term, b times y minus b times mu y. And then we have c minus c. Well, c minus c is always 0, but we're just going to write it to show you how we're regrouping these terms. So we do this, and we make an observation. Well, if we associate these terms here, addition or subtraction, this goes to 0. All right, we have that term, second term, and we have our first term. So going with the first term, then the second term, and the third term, well, the third term goes to 0, so we don't need to write that. That goes away. So if we look at the first term, well, you have an a scalar for each of these ax, and you have a times mu x. Well, we can make use of the distributive rule, factor out that common a. So we write a times quantity x minus mu x. Likewise, we do the same thing with the second term. Factor out that b. We write b times quantity y minus mu y, and all of that is squared times p of x. That hasn't gone away. So now, of course, we're going to apply the FOIL rule. So when we apply the FOIL rule, we look at this expression. We have the first term, we have the second term. So we're going to label that term 1, we're going to label this term 2. And for the FOIL rule, we said the first term, we're going to square that. The second term plus, we're going to square that. And then we're going to write plus 2 times the first term times the second term. And that was our FOIL rule, the cross terms. So we take this expression and we say the first term squared, well, that's just a squared times x minus mu quantity squared. The second term squared, that's just b squared times y minus mu y quantity squared, plus 2 times the first term times the second term. So that's 2 times a times b, and then there's the x minus mu times y minus mu y. So just multiplying 2ab, x minus mu x, quantity y minus mu y, all times p of xy. So now we take this expression and we're going to distribute this multiplication by p. We have one term here, that's our a squared x minus mu x quantity squared. We have our second term, b squared y minus mu sub y quantity squared. And we have our third term, which is a result of the cross term in the FOIL rule. That's 2ab x minus mu y minus mu y times p of x. So I'm going to distribute this multiplication into that sum of those three terms, multiplying it by the first term, the second term, and the third term. This is where it gets pretty big, but you can still follow along. So here's my first term, a squared x minus mu x quantity squared. I multiply that times p of xy. Here's my second term, b squared y minus mu y quantity squared. I multiply that times p of xy. And here's my cross term, 2ab x minus mu x, y minus mu y times p of xy. So I'm just distributing this multiplication by p of xy to each one of those terms, the first, second, and the third term. Okay, so let's write this up higher so we have a little bit more scratch space. So now I'm going to associate these sums. Instead of summing together the first term with the second term with the third term, here's my third term, and then doing this summation and then doing that summation, I'm going to do the summation for different instantiations of x and y first. And by doing that, I'm associating summations of all the first terms, all the second terms, all the third terms, and then taking those sums and then summing them. So I rewrite this as all of the instantiations of x and y for the first term. That's here. So I have my double sum for x and y, a squared x minus mu x quantity squared times p of xy. I associate all of the instantiations for x and y to the second term, right? So that's my sum over all xy, b squared times y minus mu y quantity squared p of xy. So that's here. And then I do the same thing for my third term. So I have all instantiations of x and y. I have 2ab x minus mu x, y minus mu y times p of xy. That's here. So when I look at this now, I say, oh, wait a minute. This constant here, I can make use of the distributive rule and factor this out of all the terms because it multiplies all the terms over this summation of all instantiations of values x and y. So I can bring this out, making use of the distributive rule, distributing multiplication over addition, and I write a squared, because it does not involve x and y, that's double summation of x minus mu x quantity squared times p of xy. I do the same thing here. I bring that b squared out, factor it out. So I have b squared, my double summation, y minus mu y quantity squared p of x, y. And then this 2ab, that's a constant. So I can factor this out. I write 2ab, double summation, x minus mu x, y minus mu y, probability of x, y. Okay, so now that I have this, I make some observations. I look at my expression, and this is nothing more, if I look at it, this is nothing more than a squared times the variance of x. Now, why is this the variance of x? Well, it's a very good question. If I look at this variable, this term, I notice, oh, wait a minute, this is just x minus mu x. It involves the x random variable. Mu x is just a quantity, it's a constant. And so if I look at it, nothing here involves a y. And here I'm iterating, I'm summing over the y's. So because of that, this term looks like a constant underneath that summation varying the different values of y. So I can write this expression factoring out that whole term. And I can write a squared times quantity times my summation of x with respect to x. And I write x minus mu x, and I factor that out of that summation with respect to y, and I get my p of x, y. So when I do that, I make an observation. I see this. Oh, wait a minute, that's marginalization. So I take this marginalization, and I rewrite that as p of x, because I'm summing over all those instantiations of y for that joint distribution p of x. So that gives me a squared summation with respect to x of x minus mu sub x times p of x. So if I look at this, oh, wait a minute, this expression, that's exactly, I forgot the square term, that's exactly variance. So that's the same as saying variance of x. So this becomes a squared times variance of x. I do the same thing here. I write b squared, and now when I look here, I have a summation involving x and a summation involving y. I can arrange these summations differently. So I can arrange it so that my summation with respect to y is on the outside, summation with respect to x is on the inside. If I do that, this term involving y looks like a constant underneath that summation with respect to x. So I can write b squared, summation with respect to y minus mu sub y, quantity squared, summation with respect to x, p of x, y. I look at this, wait, that's a marginalization. That becomes p of y, and that now becomes b squared, summation with respect to y minus mu sub y, quantity squared. That's nothing more than the variance of y. And so now I'm left with b squared times variance of y. And if I look at this last expression, well, I have 2ab, my double sum, x minus its center, y minus its center, p of xy. That's nothing more than the covariance between random variables x and y. So now I have 2ab times the covariance of x and y. So there's my result, and it's exactly what I was looking for. The variance of ax plus by plus c is a squared times the variance of x plus b squared times the variance of y plus 2ab times the covariance between the two. And there's my transformation. There's some other properties associated with random variables. Covariance is commutative. So that means the covariance between x and y is the same as covariance between y and x, and that's due to the associative rule, and also that multiplication is commutative. That the correlation of x and y is the same as correlation of y and x. We also have that the variance of ax plus b, where ax is plus b is a transformation, a so-called affine transformation on random variable x, any function of random variable x of this kind for arbitrary scalars a and b is going to be a squared times the variance of x. And then covariance, if we take the covariance of ax plus b, so we have an affine transformation on x, cy plus d, a different affine transformation on random variable y. The covariance of this quantity, these two transformations on x and y, is a times c covariance between x and y. And so this gives us properties that allows us to calculate what the variance and covariance is for different transformations and functions, types of functions we may apply to random variables. And then lastly, our correlation. If we have affine transformation on random variable x and affine transformation on random variable y, the correlation of those two transformed random variables is just the correlation rho between x and y. We also have that if x and y are independent random variables, covariance between x and y is 0. And then if we have the variance of x plus y, where x and y are independent, variance of x plus y is equal to variance of x plus the variance of y. And so these are standard properties, and you should become familiar with them because it will help us in our calculations for other things during the semester. Okay, so I'm going to end there, and I will see you all on Thursday. As usual, please stay healthy and stay safe.